What made that funny for me was the fact that the semester before that, Chris explicitly called out, "Don't be late, and show up with coffee," and then
Okay, so today we'll start formally to learn the conjugate gradient method. Okay. So one of our goals to learn this class is to learn the mentality of the mathematicians who invented all these optimization methods. So for example, I'm saying this is because we want to investigate, so in the steepest descent, even though this is a review, but we'll review this from a higher perspective. Okay. So again, so we're dealing with a positive quadratic function in n dimensions, and in steepest descent, we learned that this is so our algorithm. Okay. So this is our algorithm, and alpha k is chosen such that we minimize the function value along the negative gradient direction. Okay? And then we have this convergence. So x star is our minimizer. Okay. X star is our minimizer. F. So kappa is the condition number. We have this convergence result. So kappa is defined as so there's a problem with this. That is, the convergence is highly dependent on how our kappa is. So think about this. So you guys will see this in the homework too. That is, let's use x1, x2. So if we have this, that is in 2 dimensions. Okay. Hopefully everyone can already see what our condition number is for this problem. So this problem we can write it as what? We can write it as this, right? Or simply 1, 1. I mean, if we don't feel obligatory to keep the same 1/2 here, but all right. So what is the level curve of this function look like? It looks like this. So for example, this is f equals 1, f equals 2, f equals, yeah, maybe not, if it needs to be, this maybe 4, optimize this function in homework, coding homework, we will observe for steepest descent, no matter where we start, we will get to the local minimizer, this x star, okay? X star equals 0, 0 is the unique local minimizer of this quadratic function, which is pretty obvious. It will get no matter where we start, okay? So steepest descent, so I'm just using short ST, okay? Steepest descent converges in one iteration. It's pretty crazy. I mean, it's well expected because we're doing line search, right? So, because the negative gradient direction, okay, at this point is pointing toward the center. It's pretty straightforward to compute. So the gradient is in the direction of x1, x2. The negative gradient is in the direction of negative. So this is our negative gradient. You know, it's pointing, so from every point, it's pointing to the center. Okay. So this is our negative gradient of this f. So if we do a line search, I mean, line search is just to find the minimum along the line, where of course we reach the center, you know. So then, we just change the problem a tiny bit. Okay. The problem is only changed a tiny bit. We add a 1000 coefficient in front of the second variable. So intuitively, the difficulty to find the minimizer of this problem shouldn't be changed too much. So it shouldn't be changed too much. However, if we write it as, this x1, x2, okay. So by the way, the kappa in this case equals lambda max divided by lambda min is 2 divided by 2, or 1 divided by 1 is 1. Okay, so kappa is 1. So if we look at the convergence, kappa is 1 means we converge in one iteration because the next iterate already reaches error 0. Okay, so this one, things is getting interesting because kappa is lambda max of this matrix, which is 1000, divided by lambda min. So this is 1000. So suddenly, our steepest descent converges like crazy slow. Okay. Right? I mean, so if you guys have a cell phone, try to compute. So this is, if we set, for example, if we set this k equals 0, you know, so it's easy to verify that if we keep this inequality going, it will be something like this, right? So it will be something like this. Yeah, I always forgot to write this Q norm. So yeah, add this Q norm. Okay, So this is our initial error, is this is like how far our point is to our local minimizer is. Okay. So this is like our k plus 1 iterate. This is after k iterations, like the error reduction factor. Okay. So how many error is reduced? Reduction. All right. An estimate would be it takes hundreds of iterations. Okay. So then we think, oh, it shouldn't be that way, right? Because, oh, thank you very much. It shouldn't be this way because they look like the same quadratic function, don't they? It's just we had a 1,000 factor. Okay. So to explain why this is the case, let's look at our steepest descent. So from a higher perspective, okay, we still deal with that f, but what I want to point out is this proof applies. So the argument, this argument, applies to any smooth f. Okay. That is locally convex. Okay.
Excuse me. Where that power k comes from in the last line?
Okay. So this is an inequality. We can pass this inequality on, right? Because this inequality holds for any k.
Yeah.
So if we apply it twice, agree?
Mm-hmm.
And then we can apply.
Okay, what's it? Sure.
Okay. Yeah, I think this should be k plus 1. Let's make this. So our intuition is, mathematician thought it shouldn't be this way because the steepest descent, even though on paper it looks pretty beautiful, especially here, this argument. Okay, so think about this. What we did to steepest descent is we find the solution alpha greater than 0 in the following problem, that we find min of alpha. Actually, we minimize the function value at the k plus 1's iteration. We did this minimization. Because the function value of we derive the formula, it's just same thing. We search in this direction, right? Okay. Right. So this is our steepest descent. How we found alpha in the first place. This is how we found alpha in the first place. That is, we minimize our function value along the negative gradient direction. So, but now let's simply look at this formula. Okay. If f is convex, then we take any direction, we cut it, it's still a convex function, So I'm skipping this technicality, just grab the higher. So what we did is we take So if it's a convex function, find the minimum is just taking the derivative, set it to be 0. Okay. So okay, we just want to set this to be 0. Now let's take a look at, so now let's apply chain rule. Okay. Chain rule, so outer function is f. Chain rule, so this is by chain rule. If we apply chain rule, it's taking derivative of outer function. That is, we take the gradient of f of gradient of f. This is outer function. Inner function is we take derivative of this guy with respect to alpha. Okay, so it's d alpha of x k plus 1 iteration. All right. What is this? What is a k plus 1's iterates gradient with respect to alpha? It is actually the negative gradient at kth iteration. Okay. So this is what? This is, so we put the negative sign in front. This is the gradient at k plus 1 iteration, inner product with the gradient of kth iteration. And what they are? It's 0. What is this? So this is the search direction at iteration k. This is the gradient of k plus 1th iterate. I mean, which means our direction of search will be along this direction. I mean, will be negative that, but you guys get the idea. So this will be search direction at k plus 1th iteration. What this tells us is steepest descent search direction at every iteration, it's orthogonal to the previous iteration. So now let's explain why this one converges so bad. So I mean, if we plot, okay, if we plot that, so, okay, so x1, x2, so something like that. Okay. So if it's 1, x2 will be super small, right? So this is x1, this is x2. Okay. So then the so basically we learn, we learned this but even back in middle school. So if we plot the level curve, we set this to be a constant, we'll get an ellipse. Okay, because the coefficient. So we'll get something like this. Okay. So every level curve of that function looks like this, is an ellipse. Okay? So it looks like this. Now let's look at our steepest descent. If our initial guess is here, okay, the negative gradient points to the center. All right, bam, we're done. Okay, one iteration. But if we're here, all right, so if we're somewhere here, so think about this. Now the negative direction points nowhere to the center, but it rather point to this. Okay? So this is like the negative gradient. So for example, if this is our x of 0, this is negative gradient at 0th iteration. And when do we stop? Is we stop such that the next gradient direction is orthogonal to our current gradient direction. Because this is the result of the line search, is the gradient of next iteration is orthogonal to the current gradient iteration. So it should be somewhere around here, okay? So that the tangent line of this is orthogonal to the normal line over here, okay? So this will become our negative g1. Same thing. So this is our x1, and then we do x1, so we may reach somewhere here. So actually, you know, so the pattern will be like this, which will be zigzagging toward the center. So this is what steepest descent is like when we choose our initial guess here. If we choose our initial guess here, boom, it will reach the minimizer in one iteration. However, if we chose our initial guess somewhere here, then it's going to be bad. Okay. So what it tells us is here, it's highly dependent. So because of this condition number thing, because of this, so this is how we read the theorem. Because of this, this factor means steepest descent, its convergence by convergence, we mean the process of its getting to the minimizer is highly dependent on where we start our iteration. Okay. But the good news is it converges. I mean, its convergence is independent of where we start, but how fast it converges to the local minimizer depends on where we start. So this is not, let's say, not a favorable algorithm. Okay. So now let's learn, okay, conjugate gradient. So let's first say what conjugate gradient does. Okay, so like one of our textbook, this Chonzak said in the first place. So conjugate gradient, it converges to x star at most n iterations if Q is an m by m matrix. Okay. For this problem. For this problem. Actually, it converges to that in most n iterations if, not for this, but Q is strongly convex. But, yeah. But let's just still restrict ourselves. okay, in this case. So it converges to the local minimizer at least, at most, n iteration. What it means for this problem is we won't experience the case where the steepest descent, has, but rather, what happens is after it reaches here, okay, so we'll learn that the conjugate gradient, the first iteration is the same as steepest descent, but the conjugate gradient, what conjugate gradient does is for the two-dimensional problem, okay, this is a two-dimensional problem. The first iteration, it reaches here, then the second iteration, bam, it goes to the minimizer. So, but now we'll learn the mathematical tool to how to construct conjugate gradient. Okay. So to learn conjugate gradient, the first thing we need to learn is projection in a product space. So projection is an important idea or method in every applied math and in machine learning. So for example, actually so if we talk about algorithms such as image denoising, for example, in this problem, how we denoise a CT scan, or anything like that, everything is projection. So the question asked is where we project like a function of interest to, or a vector of interest to. And other things like, for example, in signal analysis for audio, for example, if we do wavelet, if we do fast Fourier transform, they are projections. It's projection to a different kind of basis, dimension reduction algorithm like SVD. So you guys may have heard of it, single value decomposition or principal component analysis. It's a projection, just to a different space. So the projection idea is everywhere. And if you happen to be trained, so I was trained in PDE, so everything is a projection. It depends on how we view things, for example. So now we define, now let's recall, so we defined earlier an inner product. So we define the vanilla inner product in Rm, okay? So the vanilla inner product is X transpose Y. So if we have two vectors in Rn, and this can be also written as X dot Y, so it's basically we're summing up the component, multiplication of these two, so we use the notation X comma Y parentheses, okay? And when we try to analyze the steepest descent, we used another projection. We used another inner product. That is, if we have a matrix Q, that is SPD, okay, so symmetric, positive, definite, so Q is greater than 0. So we have another inner product. Okay, so this Q is the subscript of this dot, but I don't like this notation. Okay, so we'll use this notation in our class. That is X comma Y parentheses. Then this Q is for the is a subscript of this parentheses, and it is X transpose QY. Okay. All right. So this is the inner product we'll be working on along our analysis of conjugate gradient. So today, I'm not sure if we have time till we reach actual conjugate gradient algorithm. But let's say, let's still do every preparation to present conjugate gradient. So first, this is an inner product. Okay. So let's use this notation. So this is an inner product on our space Rn. Okay. So it means, so this notation means it has two inputs, okay, which is X and Y. All right. So first property that inner product is commutative. This is true is because, okay, so this is true is because Q is symmetric. So the first one is true is because Q equals QT, okay? So this is because Q equals QT, so it's easy to verify that X transpose QY equals Y transpose QX. Okay? Because they are all numbers, so we can transpose them. So if we transpose the second one, we'll get X transpose Q transpose Y. Okay, they are the same, because Q transpose is the same as Q. So the second one is, this thing is positive. Okay. For any X. And if this is 0, then it's equivalent of X equals 0. This is straightforward to verify. It's actually just to apply the Rayleigh's inequality we learned earlier in this class. So, or we can, engage like an eigenvalue decomposition for Q, but this thing is greater than, so this is what we learned in Rayleigh's inequality. Okay. So the X inner product with itself in the Q inner product is greater than the minimum eigenvalue of Q times the square of X inner. So it's sure it's positive. Okay. So next two are straightforward. So next one is straightforward to verify is we have if we have this linear combination, so we can actually pull out alpha 1, x1y plus alpha 2, x2y. So this is just a linearity. The linearity in the other place, so because we have two inputs, right? The first input and the second input. And the linearity in the second input is implied by this commutativity. Okay. So this is the inner product. Okay. That's for sure. So Q subscript, Q subscript, Q subscript. Okay. So this just tells us then So if this defines an inner product, then this is a norm on I. So where the norm of X, the Q norm is defined as X transpose QX, then we take square root. So the next preparation, so this is inner product, right? The next preparation is we'll learn projection. So this is a regular two norm in this sense. Okay. We consider this problem. So S is a subspace of I. If we draw the geometric interpretation of this in 3D, think about this. First of all, this is a minimization problem, right? It's a minimization problem. It's a minimization problem. We find X such that this difference is minimized. So now we think about if this is our subspace S, okay? So if our x0 is here, this just translated to a high school geometric problem. That is, we just project this x0 here, okay, such that this line is perpendicular or orthogonal to this plane. Okay. So for example, for any x, this line is slanted. It does not have an orthogonal. It's not orthogonal to the plane of S. Okay. So this is like our x star here. So this is the geometric intuition of this problem. So actually it's kind of the same. Okay. So it's kind of the same geometric intuition with our 3D geometric intuition. So this is our geometric intuition. That is, this line, okay? This line right here, which is this vector. Okay. So this vector is x star subtract x0. Okay. Right? So x star subtract x0 is like this vector. So this vector should be orthogonal or perpendicular to the plane S. So it's equivalent. So it's equivalent of what? It's equivalent of saying this is orthogonal to any of this type of vector. So we change this x on this s. It should be orthogonal to all type of these vectors. So this vector is orthogonal to this vector. It just means x star subtract x0 is orthogonal to x subtract x star for any x on this s. So they're the same. This is the same. So these two statements are the same. Okay. What it means by orthogonal is we use inner product to translate this orthogonality. That is, x star subtract x0 inner product with x subtract x star should be 0 for any x. Next. Okay. All right. So we did our translation from high school geometry to a grad school, like optimization class. If we translate the orthogonality into inner product. All right. So how do we find this x then? All right. So we want to minimize that. It's equivalent of minimize, so we minimize. It's equivalent of we minimize. We minimize this square. We minimize the norm. It's equivalent of minimize the norm square. Okay. So how to solve this equation? We can solve this in a variational formulation. Think about this. So we define a new function, phi. Okay. Of alpha equals x plus alpha v, okay, minus x0 squared. So alpha is a number, and v is a vector in S. Okay. So think about this. So if x is in the S set, because S is a subspace, okay, so we add another vector in S. It's still in S. S is a subspace, so we cannot escape this subspace S if we add the same vector, multiply a constant to it. Linearity. Okay. But now this is a function of alpha. So this vector, what does this vector mean is, so this vector is like if we change alpha and we change v, okay, then this vector kind of changes. So x is maybe here, if we change this vector, then we're kind of searching. This is searching in this subspace instead of a line. So think about this. So if we search, so this is like a subspace search. Okay. We learned line search, right? Line search is we minimize something along a line that, but this is a subspace search. If we want to minimize this, we minimize this function in the alpha variable. So this is a subspace search. We search the minimum value of this in the subspace. Okay. So what we do, we take derivative of phi alpha and we set it to be 0. This is a quadratic function. This is a quadratic function. That means if we find the critical point, it must be the minimum, local minimum. Okay. So this is PD alpha. With this one. So this one we just rewrite it as the inner product. So all right. So we expanded the inner one. So I'll skip several steps. Okay. So this will be alpha square V inner product with V. All right. Okay. Plus. So 2 times alpha x subtract x0. V, okay. Finally, we plus what? We plus x subtract x0 times x subtract 0. So I mean quadratic formula. Okay. So we group everything with alpha in one term. So for example, we combine this and that, and then this term has alpha, and the rest is x subtract 0. So we'll have this quadratic formula. Okay. So now if we take derivative, we will get, this is what? This is 2 alpha V inner product with V plus x subtract x0 inner product with V. The final term doesn't have alpha, so it's gone, right? And we want to set this to 0. Okay. And what's interesting is, so at
Have you missed
Miss it
2?
too, yeah,
Have you missed
isn't there
2?
gonna be a constant in front of it?
So if our x is our x star, which is a projection of x sub 0, okay, so this is our local minimizer. That is projection of x0 onto the subspace S. What happens is, if x, okay, is our local minimizer, that just means this term should be 0. Okay. So that means what? That means phi alpha minimum is achieved at x equals x star, alpha equals 0, and for any v in this S. Okay. Now we just plug it in our formulation. Alpha 0, x is our x star. Okay. So we get an equation. In linear algebra, I assume everyone is expert in linear algebra. Actually, we already learned this in linear algebra. Matrix multiplication is a projection. It's project into the column space of that matrix if we multiply a vector. So this is the same. Okay. So let's look at this subspace. Now, if we rearrange the term a tiny bit by linearity, this is the same as x star, which is our projection, inner product with any vector in S is x0, inner product with any vector in S. So this is for any v in S. So now we define our definition of our projection. Definition, projection. In the L2 norm, okay, or say in the vanilla inner product, so this is a vanilla inner product with Rn. Okay. That is given x0 in Rn. Okay. So the projection of x onto S. So S is a subspace of Rn. So S is a subspace of Rn, and the projection of x0 onto this subspace, which is denoted by, so this notation. You guys must have seen this either in vector calculus or in linear algebra. Okay. So the projection of this x0 to this subspace S can be obtained by the following. Can be defined as so this projection is just our x star. It's like the distance of this x0 to that is minimized. So the projection x0 inner product with any v is x0. So the projection inner product with v is x0 inner product with v for any v in this subspace of S. Okay. An equivalent definition is the projection minimizes the distance. That is, the projection, okay, the projection subtract, so this is our projection, subtract x0, minimize is a minimized distance, minimum possible distance of all element in S to this x0. So this is our projection. All right. Now we ask ourselves, okay, what is the usage of this? Okay. So let's back to the figure where steepest descent we had. Okay. All right. So let's back to the figure of steepest descent we have. And this is our quadratic functions. For example, this is f equals 1. The the minimum value is the center, which is f equals 0. This is f equals maybe 9, f equals 25, or whatever. But this is the level curve of this f. We start from here. We start from here. And we minimized something, right? So remember, so let's recall an identity. Let's recall an identity that this is 1/2. Okay. If this is k plus 1's iteration, this is k plus 1's iteration. Okay. Now think about what we're doing in steepest descent. Okay. So if we follow the negative gradient. So if this is xk's iteration, we follow the gradient, negative gradient at the kth iteration. And we stopped whenever, we find out it's orthogonal to the k plus 1 iteration. Okay, so we stopped here. We minimized something, right? So we minimized something, so we minimize function value along this direction. We did a line search. Okay. So if we translate to a subspace search, so the subspace dimension is 1. Okay. So here comes our conjugate gradient. What if I tell you that we can enlarge our search space? Okay? Remember, the problem of we're going in this narrow alley is every time the search direction, the search subspace dimension is 1. What if I tell you that when I do first iteration, so we search in the subspace dimension 1. What if when we do the second iteration, we search in the subspace of the dimension 2, and we go on? So when we have a dimension m by m matrix, when we search, n times, we search n direction, right? So if these n direction happens to be a basis of our whole space, okay? Let's think about this problem. If our search space is whole Rn, what would this be? So what is our local minimizer to minimize this? It should be x0. So this is a difference of x with x0. This is 0 unless x is x0. So the minimizer is x0. So when our search space is enlarged to the whole Rn, we will sure get the minimizer if there exists one. Okay? So this is the basic idea of conjugate gradient algorithm is steepest descent every time we have a dimension 1 search subspace. Conjugate gradient, we enlarge the search subspace in every iteration. So next topic is how do we view this search subspace? So here is so this will be our homework in our homework 3, which is about conjugate gradient. So first we have verified that oh, I already erased it. So we have verified that this QSPD, okay, so is an inner product on Rn. And conversely, this defines a norm, okay? Okay. So next is we define projection. In this Q norm, or say Q inner product. So same thing, okay? So the projection, let me look at the notation, I just want to be consistent. Okay, so I use the superscript. So the projection in Q is, given, again, given this, okay, so any element in Rn. So later we will see this is nothing but our, local minimizer. So, and S is again a subspace, right? So setting is the same. It's just the formula is slightly different, and the projection onto S, but with respect to the Q inner product, is basically denoted by this. Okay? So this is defined as this guy inner product with V, but in the Q inner product is the same as X sub 0 V Q inner product. So we will see that this is the same thing as we minimize the distance in the Q norm. That is the projection of S of Q. This subtract X0 in the Q norm is the minimum of all X in this subspace. Subtract X0 in the Q norm. this is for any D in this S. Let me stop here because the next derivation is kind of long. So next topic will be how to build this subspace. So next topic is how to build the search subspace. And this subspace, this idea is also one of the, more advanced idea in machine learning optimization. Those advanced algorithm is we have to take advantage of our optimization algorithm because we are running iterations, right? So the steepest descent is like every time we discarded the information from previous iterations, okay? But this tells us, okay, so we should record information from every iteration to guide us, to the minimum. But next time we'll learn how to build the search subspace. Okay?
Thank you.
It's not posted yet. Yeah.
কি বলছো?
Is it kind of definition that was like defined like
Yeah,
this?
it's fine.
Okay. Okay, now I'm just gonna look like how the queue is going to change the thing. So
Yeah.
every time we see this, it's going to this.
We define it like this way, and we then verify it's indeed.
So if we don't have this queue as subscription, we'll just ignore that.
Yeah, normal.
Thank you.